This is the third section of the Taylor series chapter 6, and here we're going to be looking at this series solutions of differential equations. So a differential equation, we'll start with a first order differential equation, and I'll just put DE for differential equation. In its simplest form, all we need to do to solve a first order differential equation is to integrate it. So we'd have something like dy dx equals some function of x, and then all we do is integrate it, and we'll get a constant of integration once we integrate it, and then we find c, put c on the end, and we have our solution. So we'll end up with y equals something, and we would have worked out a constant of integration given some values of x and y, and that solves it. And you would have learnt about this in Pure 1. I'll put a link to it at the bottom. I think I've got a video on Pure 1. If we step it up a bit, and we have a first order differential equation of the form dy dx equals a function of x and a function of y, like this, multiply together, then we can solve this and again find what y equals by using separation of variables. So separation of variables, and you learn about this in Pure 2. So again, I'll put a link for that. And then the third way that you would have learnt to solve a differential equation is where you've got a differential equation of this form, dy dx plus a function of x times y equals a different function of x, and we can solve this by using the integrating factor, and this is something you would have learnt about in Core 2. Okay, now it may be that we can't use any of these methods to solve a first order differential equation, and we can use Taylor series actually to help us solve these first order differential equations, and actually not just first order but second order differential equations. And actually I think what we'll do is we'll just have a quick look here at what you would have learned about solving second order differential equations. So I'll just put second order DE, and one you would have learnt about in Core 2 would have been where you find the complementary function and the particular integral. That's if it's non-homogeneous second order differential equation, and you would have learnt about that in Core 2. And actually you would have learnt how to solve second order differential equations in applied, because when you had, let's say, the acceleration, which was given as a function of time, and you needed to find the displacement, let's call that displacement S, then what did you do? Well, you would have integrated the acceleration twice, found the constants at each stage, and then you've got an expression for the displacement. Now S looks like a 5, that's actually meant to be an S, so it could be S or X, still looks like a 5. And if we use alternative notation, again we may have had the acceleration given like this as a function of time, and we find x. So that is solving a second order differential equation, because what you're doing is you've got something where you need to integrate twice to find either x, in the case of mechanics type questions, acceleration, velocity and time, or you're finding y in the case of these where you've got dy dx type questions. Now, what if we cannot use any of these methods? I suppose I should put stats and mechanics here. And again, I'll put a link. So I'm going to have lots of links in this video. So stats and mechanics, and you do that in 1 and 2. So this is stats and mechanics 1, and then this is stats and mechanics 2 when you learn about integrating vectors as well. Yeah, so what if we cannot use an algebraic method and we need a different method? Well, this is where Taylor's series comes in, and it's really useful. So when we solve either a first order or a second order differential equation, what we're trying to get to is we want to get this, y equals something. Okay, that's what we want to get to. Now let's think about what Taylor's series looks like. So Taylor's series is actually y equals, well actually let's start by writing it as a function. So we'll move to y in a minute. So let's just start by what we know about Taylor's series. So f of x equals, well, what do we have? The function about a plus the first derivative of the function about a times by x minus a plus the second derivative of the function about a divided by 2 factorial times by x minus a all squared, and so on. Well, when we're trying to solve a differential equation, we're actually trying to find f of x, which we can call y, can't we? So let's now write y equals. Now, what does y equal? Well, it equals the actual function itself when we substitute in a. So maybe at this point, I'm going to introduce some notation, 1 or 2 other things to do with these differential equations. The first thing is that often in these questions, and actually you would have done it in these types of questions here, and with the mechanics questions, and with the second order differential equations in core 2, is that you were given some values of x and y that allowed you to work out what the arbitrary constants are. You were given some values of x and y, and these given values of x and y can be called initial conditions or boundary conditions. Okay, so we are given values of x and y, sometimes just x, and you need to work out y, of x and y, so that we can starts with a C, not an A, so we can calculate the value of the arbitrary constants, constant or constants. There could be just one, there could be more, and these are called, as I said, either initial or boundary conditions. And we're going to call these, in these types of questions, we're going to call these values of x and y that we've been given x0 and y0. So we're going to be given these. So these are initial values that we've been given. Now, when we apply this to the Taylor series, our A is going to be x0. So that means that f of A is going to be y0, yeah, because it's that particular value of x that gives us that value of y. So A in our Taylor series, Taylor expansion, is going to be A0, the initial or boundary condition we've been given for x. Sometimes it's 0. And f of a is going to be the initial boundary condition we're given for y. Now, you can see that, well, this will be y0 here. And this will be the first derivative with x0, y0 substituted into it, and so on. Now we need a nice neat way of writing that. So I'll write it over here. If I were to write something like this, dy dx with a line and with x0, this basically is shorthand to say that we're going to sub in the initial or boundary conditions into dy dx. So substitute in the x0, comma y0 into dy dx. Similarly, if I have d squared y over dx squared, again with this line here and at x0 at the bottom, this means that I substitute in the x0 and y0 into the second derivative, d squared y dx squared. Now that matches up with Taylor's expansion, because that's exactly what this would be here. So we can now rewrite the Taylor series, the Taylor expansion, like this. So f of a here, well, that's just our y0, our y initial condition. So we'll just write y0 plus, now this bit here, what's this? This is the first derivative with a substituted in, our initial condition, x0, y0. So the way that we write that, instead of f dash a, we write dy dx, that's the same as f dash, with this line, and the x0 here means we substitute in our initial conditions. Now this gets multiplied by x minus a, so x minus, now a, remember, is x0, like this. Now what I think I might do to avoid any confusion is just write this the other way around. So I'll put the x0 at the bracket part, the x minus x0, I'll put that at the start, and then the dy dx. Okay, so I've just swapped the order. Then the next term, well, that's going to be, again, I'm going to swap the order. It just makes it a bit easier to write it over 2 factorial. So x minus x0 squared. Okay, so that just matches up with this bit. I'm going to write this over 2 factorial, like this. And this gets times by the second derivative, f double dash of a. And the a is x0, so this means substituting the initial conditions plus dot dot dot. Now what we have here is a Taylor series, or a Taylor expansion. So I'll write this down, a Taylor, let's spell his name correctly, not Taylor, a Taylor series about x0, okay, which is a series solution. So it's a solution to a first order or even a second order differential equation, or a high order or higher order differential equation. So a Taylor series about x0, which is a series solution to a differential equation of the form dy dx equals some function of x and y. Okay, with initial conditions x0, y0. So this gives us another way of finding a solution to a first order or second order or third order higher order differential equation, but not an exact solution, a series solution. So in other words, the more terms we write down, the more accurate our answer is going to be. And quite often in these questions, we'll probably only go up to maybe the x cubed term. Now I mentioned a bit earlier that sometimes x0 is equal to 0. Now if that's the case, if x0 is equal to 0, then what happens in expansion, let's see if we can do this in green as well, is that these will just be 0 here, like this. So all of those x0s will just be 0. And our expansion basically just becomes a Maclaurin expansion or Maclaurin series. So it reduces to Maclaurin series. So just remember that it just means there's less for you to write out if that's the case. Yeah. So what will happen is any bracket that's got x minus x0 in it to whatever power will just become x to the power. So that'll just save us a bit of time. Okay, so it says here use the Taylor series method, which is what we've just been talking about. Taylor series method to find a series solution in ascending powers of x up to and including the x cubed term. So we're not going to go any further than the x cubed term. We've been given this second order differential equation, and I suppose the first thing we're going to do is to write down, just remind ourselves what this is going to be. Now notice that x0 is 0, so this is going to reduce the Taylor series down to the Maclaurin series. So our series solution is going to be of this form: y equals y0 plus x, so we don't need to write x minus a or x minus x0 because x0 is 0. That's going to be times by the first derivative, in which we substitute in our initial conditions, plus x squared times by the second derivative, in which we substitute in our initial conditions, and I almost forgot about dividing by 2 factorial here, and then plus x cubed over 3 factorial, and then the third derivative, this is as far as we go, in which we substitute in the initial conditions. Okay, so that's as far as we need to go. So we're just going to put that there as a reminder, and from the question we'll just write down the information that we've been given. So x0 is 0, y0 is 1, and we've also been given that dy dx equals 2. So the rest really is just about substitution into this expression. It's actually not that difficult. I think we've got one differentiation to do, and that's pretty much it. Right, so first of all, y equals, now y, I'm looking at what's in blue, y0, which is 1. Then plus x times by dy dx with x0 substituted. Well, you can see that dy dx is just 2, so even if I substitute in my initial conditions, there's nothing to substitute in, it's still 2. So then we got 1 plus 2x, so dy dx is 2, and it's just x. Now we move on to the next term here. So this is x squared over 2 factorial, and that's going to get times by the second derivative with the initial condition substituted into it. Okay, so maybe we'll do that over at the side here, over here. So we've got the second derivative, that is y minus sine x. So if we substitute that in, so we substitute in basically the y0 and x0, so I should actually write it like this to show that's what I'm doing. So that is 1 minus sine 0, so you just substitute in the 0 and the 1. Sine 0 is 0, so it's just 1. Right, so now I'm ready to do this bit here. So all of this bit here is just 1. Okay, so 1 times x squared over 2 factorial. So you could just say half x squared. So plus half x squared, or x squared over 2. It doesn't really matter either way. Then we move on to the third and final term. So that's going to be x cubed over 3 factorial. And then it's going to be the third derivative with the initial condition substituted in. So the first thing we need to do is to work out what is the third derivative. We've not been given that. So we need to differentiate this. The way we're going to differentiate this is we're going to use implicit differentiation, and implicit is what you learnt in pure 2. So the third derivative is equal to y will become dy dx, and sine, when we differentiate, will become cos, so it stays as minus cos. So I'll just put a note here that we used implicit differentiation, and that is in pure 2, so I'll probably put a link to that as well. So there we've got our third derivative. So now we substitute in our initial condition. So we write it like this. So that will be dy dx. Now dy dx we've been given, it's just 2, isn't it? So dy dx, we just put 2 there. 2 minus cos x, that's x0, isn't it? And x0 is 0, so cos 0. Right, now you need to be careful. Easy mistake to make. Cos 0 is 1. Yeah, cos 0 is not 0. So it's 2 minus 1, which is 1. Okay, so all of this bit here becomes 1. So 1 times by x cubed over 3 factorial, or we could write it as 1/6 x cubed plus dot dot dot. So this represents our series solution to this second order differential equation. So I'll just highlight that, and then we'll move on to the next example. So given that we have this second order differential equation here, now this looks similar to something that you might encounter in pure 2, sorry, not pure 2, core 2, and you'd start by finding the auxiliary equation, but you can see that the form it's written in is not going to be something that we can do that with. Yeah, so similar to a core 2 type question where you'd form and solve the auxiliary equation, but because we've got this xy, it can't be done. So that's why we're using the Taylor series to do this. Now it doesn't actually say Taylor series, it just says A series, but we know it's going to be the Taylor series. We're going up to the x to the power 4 term, which is 1 higher than what we're used to. Here we've got y0, which is 1, and x0, which is 1. So the first thing we're going to do is we're going to write down that Taylor series. So as a reminder, so y equals y0 plus, then it's going to be x minus a, then dy dx. I'll probably just write the first couple of terms out, and then x minus a squared over 2 factorial and then the second derivative with our initial condition substituted in. Okay, so the rest of this question is just substitution and probably a little bit of differentiation, I think. So y equals, so y0, well that's just 1, plus x minus a. Actually, I should have written, rather than a, x0 here. So x minus x0, so x0 is 1, so x minus 1, and that's times by dy dx at the initial condition. So there we go, it's just 2. So it's going to get times by 2. I will tidy this all up in a moment. Plus, so moving on to this part here. So this will be x minus 1 all squared over 2 factorial. So x minus 1 over 2 factorial, which is just 2, times by the second derivative with the initial conditions substituted in. Now to do that, all we're going to do is rearrange this and put the initial conditions in. So let's do that over here. So I'll have 2, or d squared y over dx squared equals xy minus 2 dy dx. So let's write down what that becomes with the initial conditions substituted in. Now here I could write x0, or I could actually just write the number 1 down here to show that I'm substituting in x0. So yeah, x0 here, or 1. I will put x0. So you could put 1 instead. So that will equal xy, so that's my initial condition, so that's going to be 1 times 1, minus 2 times the second derivative, sorry, the first derivative, now that's just 2, so it's minus 2 times 2. Minus 2 times 2, so that gives us 1 minus 4, so we just get negative 3. So all of this part here just becomes negative 3. So let me put my squared there. And that's all going to get times by negative 3. So now we're going to move on to our third derivative, which would be like the next term there, which means we do need to differentiate the second derivative. So that means we need to differentiate this, and we're going to use implicit differentiation for that xy. So d cubed y over dx cubed. So the xy is like the product rule and implicit. So that will become x dy dx plus y. Then yeah, if you differentiate this, that just becomes the second derivative. So that will become minus 2 d squared y over dx squared. Okay, so now we substitute in our initial conditions. It's cubed, so I'll write x0 down here. So if we do that, then this x here just becomes 1, and then dy dx, that becomes 2, so we have 1 times 2. So some very easy maths here. Plus y, so that will be plus 1. Plus 1. Then minus 2 times the second derivative. Now we worked out the second derivative up here, didn't we? That was minus 3. So it will be minus 2 times by this, which will be minus 3. So minus 2 times by minus negative 3, I should say, really, shouldn't I? Okay, so if we work that out, that will be 2 plus 1 plus 6. My maths is right. So that will give me 9. Okay, so I've now got that value. Right, so where have we got up to? We're now up to the third derivative, right, the fourth term of this series. Let's do it down here. So plus, and then it will be x minus 1 cubed over, let's put 2 factorial here, so 3 factorial, then times by 9, then plus, so we now need the fourth derivative, so x minus 1 to the power 4 over 4 factorial. So we need to work out what we need to multiply this by. So we need to differentiate again to find the fourth derivative. Let's do that. Got a bit of space down here. So d4y over dx4 will equal, now we'll use the product rule for this and implicit differentiation. So that will be x times by, well, dy dx differentiated will become d squared y over dx squared plus, and then we will have, we differentiate that, times it by that, so it's basically 1 times dy dx. So dy dx. So that's this part differentiated. The y differentiated will become dy dx, so plus dy dx. Then we come to this part. So if we differentiate this, this will just become the third derivative. So it'll be minus 2 times the third derivative. So minus 2 times by d cubed y over dx cubed. So now we'll substitute in our initial conditions here. So I'll just put x0 here. So let's go through this and work out what it's going to be. So x, which is 1, so 1 times by the second derivative, which we worked out, which was negative 3. So this part becomes 1 times by negative 3. 1 times negative 3. Then we're going to add dy dx. Now that's just 2, and add dy dx again. So I'll just put plus 2 plus 2. So plus 2 plus 2. Let's seal this off out of the way so there's no confusion. Yeah, so we've got to here, this bit here. So the next bit is minus 2 times by the third derivative. The third derivative was 9, so it's minus 2 times by 9. So minus 2 times 9. So let's work this out. So this will be negative 3 plus 4 minus 18. So that minus 3 plus 4 is going to be 1. 1 minus 18 is going to be negative 17. We've got negative 17 there. Right, so now we're ready to just times this by negative 17. Dot, dot, dot. Because that's our third derivative after, or sorry, our fourth derivative once we have substituted in our initial conditions. So now it just needs tidying up for our final answer. So 1, then we've got 2 times by x minus 1. So we'll just leave that as 2x minus 1. We won't expand the brackets. Then we're going to have this bit's going to get times by negative 3. So basically, actually, let's write this as a negative then. So that would be minus 3 over 2 x minus 1 squared. The next term is going to be positive, and then this is 6. So 9 over 6 reduces to 3 over 2. So that will be plus 3 over 2 x minus 1 cubed. And the last term, that's going to be like negative 17 over 4 factorial Our 4 factorial is 24, I think. So it's going to be negative, so minus 17 over 24, and then x minus 1 to the power 4, and then plus dot dot dot. So this is our series solution to that second order differential equation. So we've got here, given that y satisfies this differential equation here, so let's highlight that. And we've got our initial conditions, y0 equals 1, x0 equals 0. So we know this is going to reduce down from a Taylor to Maclaurin. So we'll write that down in a moment. Find a series solution for y in ascending powers of x up to, we're going up to the x cubed term. So let's just write down the Maclaurin expansion just to remind us. So y equals y0 plus x times by dy dx plus x squared over 2 factorial. We should put in that it's the initial conditions, yeah, so we should put that in as well. And then plus x squared over 2 factorial d squared y over dx squared x0, and so on. Right, so let's see what we can write down. So y equals y0, we'll write it straight away as 1. Then plus x times by dy dx. So x times by, so we need to work out what dy dx is at 0. So dy dx at its initial conditions. So you could put x0 there. Or we could just put the 0 there to show that that's what we're doing. Substituting the initial conditions will be y squared, so that'll be 1 squared, y0 squared, minus x0, which is 0, so that's just 1. So we can write down, we're going to times that by 1. Next term is going to be plus x squared over 2 factorial. Now we're going to need to work out what we multiply it by. So it's going to be the second derivative at its initial conditions. So we're going to differentiate our dy dx to get the second derivative. So we have y squared, using implicit, that will become 2y dy dx. And then the minus x will just become minus 1. So let's now work out what it is at our initial conditions. Let's just put 0 here. So that will be 2 times by y, that is 1, times by dy dx, which we've just worked out, is 1 minus 1. So that's 2 minus 1, so that is just 1. So this x squared term is just going to get multiplied by 1. So the next term is going to be the x cubed, so that's x cubed over 3 factorial times by, so we need to find the third derivative. So we differentiate our last one. Now we can use the product rule. This bit is going to be like our u, this bit is going to be like our v. So that will give us 2y times by v dash, so that'll be d squared y over dx squared, you just differentiate that. Then plus, so now we work out u dash, that's just going to be 2, but 2 dy dx. When you differentiate 2y, it'll become 2 dy dx, not dy dy. And then, so that's our v dash times by v. Did I say v dash? I meant u dash, dy dx, which is this bit here. So I will just write down here. So there's our u, this bit is our v dash, this bit is our u dash, and this bit here is rv. Then we've got -1, which we differentiate, which will just disappear. So now let's sub in our initial conditions, which is that x 0, 0 and 1. Right, so we'll get 2 times by y, which is 1, times by the second derivative, which is just 1. Okay, so all of this here, 2 times 1 times 1, plus 2 times the first derivative, which is 1, times by the first derivative again, which is 1. So that just becomes 2 plus 2, so that becomes 4. So that means we just times the x cubed term by 4. And we're done. All we need to do is to neaten this up a bit. So y equals 1 plus x plus x squared over 2, or half x squared. We could leave it as 2 factorial, I suppose. But actually, I think the next time will simplify. And then plus, now, here we're going to have 4 over 6, which reduces to 2/3. So we could write this as 2x cubed over 3, or 2/3. X cubed doesn't really matter. So there we go. So this is our series solution to this first order differential equation. You should now be able to do exercise 6c on pages 142 to 143. We'll do a quick recap here of what we've done. So basically we can find these series solutions to first, second, or even higher order differential equations. And all we need to remember is that we have x0, y0. These will be our what are called initial or boundary conditions. I should mention here maybe that we're finding series solutions to maybe first order differential equations like this. So this just means they're a function of x and y, or it could be a second order, for example. So some sort of function of x and y. Yeah, so we've got our initial conditions. We also need to know that if we see this notation, okay, or if that for a high derivative, all that means is we're going to substitute x0 and y0 into dy dx, or d squared y over dx squared. So a Taylor series expansion would look like this. So y equals y0 plus, then we'll have x minus x0 times by dy dx with our initial condition. And I'll just do one more. X minus x0 over 2 factorial, and then the second derivative with our initial condition. And the Maclaurin, let's spell his name right, let's give him some respect, AU. So this will be when x0 equals 0, then the Maclaurin expansion series will look like this: y equals y0 plus x squared, or sorry, x dy dx with our initial conditions, plus x squared over 2 factorial d squared y over dx squared. And of course these are infinite expansions, but we're only required to write a finite number of terms. Writing an infinite number of terms will take you quite a long time.